Dear students, welcome to the knowledge series. We will be discussing on Perceptron in this segment. Before that, let me give some idea with respect to our last discussed areas on separations, or what we call as linearly separable conditions. Now, in the linearly separability situations, we have seen that it's the concept to separate the input space into a region, and that is based on whether the network responds on the positive side or a negative sides. So that is we term it as a linearly separable. Now this linearly separable is what we have been using in the machine learning. Now what is machine learning? Machine learning is an applications of artificial intelligence, and that provides the systems or the ability to automatically learn and improve the experience without being explicitly programmed. So basically the machines will automatically learn and develop itself. Now here, if you try to see the sensor view the outside world, and it captures the image, and it is being processed, and finally the future is being extracted, and that extracted future is being compared with the set of database, and once the database is being matched based on its test and trained data set, then that model will try to deliver the output appropriately. So this is what we have been using in the case of a machine learning system with respect to the classifications. Now the classification plays one of the important components in the neural network. So if you look across the neural network development made by the several great scientists and developers who created the wonders in the neural network domain. So we will see, because the discussions with respect to our Perceptron will take a turn based on this study. Here, as you know that when we talk about a neural network, a neuron is normally considered as an adaptive element. That means in the neuron, what we have a weight, and that weight we have to modify, and it can be modified depend upon the input signal it receives, and what the output value it is going to produce. So if there is a matching between the output desired output with the actual output, then there is no need to go further. But if it is not matching, then there is some need to adjust certain elements so that after the further process it can able to give the desired output. Now here we start with the Donald Hebb. Now Donald Hebb, he developed in the year 1949 in the about the study of brain as well as its learning ability. So in the brain, the learning is particularly done by change of a synaptic gap that we have seen in the neural network, that based on the strength of the given input, the synaptic gap can be overcome. So that's how the brain tried to learn. Now he was the first person to comment upon this, and Donald Hebb, he was a psychologist. When he was working in the area of the neural network with respect to the brain study, he said that neuron that fires together, wires together. That means if one neuron fires, after that it will automatically transfer to the next neuron. That means that is what he says. When the neuron that fires, where the firing is taking place in the synaptic, So in the synaptic, when the firing takes place, then it builds another connectivity. So that means it is forming a wire link. Now, further, if you go to the Donald Hebb further study, he has his hypothesis with respect to the brain. It says that increase the value of the weight if the output is active, and when the input associated with that weight is also active. So that means he was stating that, or he was presuming that output W, that is output, can be modified based on the modification of the given input. That means he was stating with respect to how to improvise the given input so that the postsynaptic or the synaptic firing can be taken place in a better way, or in a faster response, so that the learning can be improved better, or the learning can be enhanced at a faster rate. So he could able to even state in that area of the study with his work that he has given to the research for the researchers to further dig into. Now if you go to the next personality, he is Frank Rosenbelt. We will be talking about Frank Rosenbelt study as a lot. Frank Rosenbelt is a psychologist, and he had published the first model of the perceptron in the year 1957. That is he is the first inventor of the adaptive network. And this work was basically towards modeling the brain in an attempt to understand how the brain can able to learn, how the brain can able to understand, and the cognitive processes. So this is the area where the Frank Rosenbelt worked. So Donald worked on the brain study. Rosenbelt went further with doing a modeling with respect to that brain study using a mathematical functions. And if you see this one, there is an arrow I have shown across. I will talk about this arrow in the point of my discussions. Before that, let me talk about half and withdraw. So this half and withdraw, or Bernard withdraw, and Martian half, they are from the Stanford University. They developed a model, what is called as Adeline and Madeline, in the year 1960s, and that recognized for the binary patterns. So binary pattern recognitions, again with respect to the linearly separable study we are going into. Now here, the two of them, they work together to further study on delta rule. Delta rule means the least mean square error. How we can minimize the error between the nonlinear components. And that delta rules are as a least mean square rules, and that was applicable for the supervisory training in the neural network. So you have to remember that the perceptron that we are going to study, it is basically related to the supervisory situations, or we term that it is a supervised learning network. Now here the two personality, one is Roman Halt and another is McClelland. These two personality in the year 1988, they developed a model which Donald Hebb has created. They created a Hebb net based on the work of the Donald Hebb, and this net consists of a single layer feed forward neural network, and where they consider the bias value as 1, and the input and output pattern, they used a bipolar activation functions to study. because the Hebb net it does not learn with the learn the if the input and output is in the binary form. So that's why this particular study of the Hebb net, what they developed, got certain limitations with respect to that. Now coming to the next discussions on the Marvin Minsky and Seymour Papert. They are the one who initially took the work of the Rosenwald in the area of the perceptron, and they published a book on the perceptron and introductory to a computational geometry. So of course the Rosenwald initially published the first model of the perceptron in the year 1957, but they work on finding all the good points and what are the shortfalls in the Rosenwald area of work. Thereby, particularly the Marvin Minsky, he tried to show how the AI concept can solve the problem of the classifications to overcome the certain limitations or the certain linearly separable unconditional situations exist in the case of the Rosenwald work. Or we can say that the Rosenwald area of the work which Marvin identified that there was needed a certain corrections, that area Marvin Minsky started working over it. However, both of them took work together to publish the book in the area of the perceptrons. So these are the area where we can see the one side it is a brain study, another is the brain modeling, the third is the third area. You can find that a work with respect to Adeline and Mandeline network, and another we can see the HebbNet development, and further we can see that the enhancement of the perceptron was carried out. So this is how the people started developing and working together for improving the level of the neural network. Now we go to the perceptrons. This is the area. Now this is the perceptron area, which was the model study was made by Frank Rosenwald in the year 1957, and this was the paper that was published. You can see that the perceptron, a probabilistic model for information storage and organizations in the brain. Frank Rosenwald, Cornell Aeronautical Laboratory. So this is in the year 1958, volume 65, number 6, psychological review, in which it was published, and that work has given way to the circulation in the newspaper. That is what you can see over here in the New York Times, July 8, 1958. This was published. Now here, one thing you can see this one, a perceptron model. If you want to understand, it is better. Let us see this particular understanding using the figure I have displayed here. Now, in this particular figure, you can see that a simple perceptron model, which is being shown over here, it was first created by the, or first published by the Frank Rosenwald, and it is the first active neural network architecture. And this particular model was a replica of the brain in an attempt for people to understand the memory and its learning and its cognitive processes. So the figure with respect to Mark 1 perceptron is being shown here. Now in this Mark 1 perceptron, you can try to see that here a sensor grid is shown, and this particular grid is shown in the form of a alphabet is shown, S is being shown, and this particular grid, it is a 2D matrix, and it has having a 400, nearly 400 photodiodes. So this 400 photodiodes matrix is being created at the input sensory unit, or we can say sensory unit or a sensor grid for representing the pattern. Now this input pattern is being fed to the association unit. Now what exactly is the association unit? It is the set of nodes. You can see in my next subsequent figure. So here we will be using a neural network nodes, that is the associations layer, and further these nodes is being fed to the response layer. This is also the output nodes. Now here for your understanding, for the detections of the input, we are using a norm that a binary 0 and a binary -1 and a +1 as a weight value for this given input. That is what been shown as the number of input that has been fed to this association layer. Its weight is being distributed as 1, 0 and -1, and the association layer is basically a future predictor. Future means this S is a future, and based on that future you have to see the response layer. It is going to produce a exact S, and that is being labeled as S. That label S is identified as the output. So here the association layers, which is a future predictor, process this input and it is mapped to the output layer, and output layer is going to produce a response 0 or 1, whether it is yes or no with respect to the given input. Now if you look further, this is what we talk. When we talk about a sensory grid, it is being represented in these forms, and here this is given as a x1, x2 up to xn, and where we are taken a bipolar binary input. See, binary is a 0 and 1, but we are taken a bipolar situations. That's why it is 1, 0, -1, bipolar situation. x1, x2, xn is nothing but association unit, and the response unit, which is the output, is nothing but y1, y2 up to yn, and every node is been connected together with its weight, which is having a 0 and 1. So here from the input side a weight is being shown, and in the output side also a weight is shown, which is between this node to these nodes. So that's how the output is being produced. Now what is the output? Output is shown as 0 and 1. Now here if you try to see this y is nothing but a predicted output. So this is the predictions we have got. But if you see here, what is the desired output? It is denoted as T1. So if our output is not same as the desired output, then it is going to generate a error. So that generated error, it is being used for the further enhancements of the input. So for every node a separate error is being shown over here. That is what being shown by the shown in the Mark 1 perceptrons by the Frank Rosenbelt. So based on this study, we will see the mathematical functions. What the mathematical functions with respect to this one it signifies. Now here it shows the input, which one shown over here as x1 to x1, xn, and w1, w2 up to wn. That is what being shown over here, and y is nothing but a bias, a separate bias is being shown, and the final output. So let us take under this particular situations. Now under this particular situations, if you are taking the x1 is taken, is added with w1, x2 with w2, x1 with xj with wj, xn with wn, b with 1. So this entire thing is summed together. So so here what we have seen is nothing but here there is no weight. Here this is the only input is being given. Here only the we are seeing. So this weight is what we are seeing here. This exactly, and here is being this all grid point is given as an input. So that's how this x1, x2, xn is being represented here. So for your understanding, there is no weight. So there is no hidden layer. There are only two single layers. So this is input and this is output. So this is input and this is output. So here all this thing it is being summed together and given to the activation function for delivering output y. Now let us see that representation in the mathematical forms. Now here what is happening here, the sensory unit is connected to the associated unit having a fixed weight of 1, 0 and minus 1. That is with respect to the activation functions. What we will be seeing with respect to this sensory unit is connected with the associated unit. Now a binary activation function is used with the sensory unit and the associated unit. So that is what here it is being termed. And the response unit has an activations 1, 0 and minus 1. So this 1, 0 and minus 1 is the one which we are going to use it for identifying this the final response. Now when we are taking this input at this particular point, what is the y in? Y in is nothing but summation of all. So that is we termed as y is equal to f of y. Now f of y is when it is going passing through the activation function, it has to produce 1, 0 and minus 1, and that is going to produce how 1, 0 and minus 1. It is based on these conditions. If it is 1, then y in should be greater than theta, and if it is minus 1, it should be less than theta, and it will be 0 when it is lying between minus theta and theta. So that is the conditions that we are creating over here for identifying the value of y. Now here you have to see this one is that the weight updations of the perceptron is shows the learning. That means here the actual weight or the predicted weight and the desired weight. So that is a targeted weight. If there is a variations, so that variation is going to represent in this way. So y is not equal to t. If y is not equal to t, then what is going to happen? You can see that the weight is going to modify. You have to change you have to modify this weight. Now how you can modify this weight? This modification of the weight is possible by two things. One is alpha, another is t. Alpha is nothing but a learning rate, because the system has to learn. That's how the weight is being adjusted. Now the system has to learn, so that's how that's what it is represented in terms of alpha, which is a learning rate. Another is a target. So whether the achieved target is being attained or not. So based on this alpha t and the input x value, we can able to create a w new, and this w is the old weight. So that's how it will be able to create a w new. And you can also see that a b new is also created, bias new, that is also bias old plus alpha into t, because here you will not find x, because we have already taken the b bias plus its learning alpha into t. So there itself is we are considering the b as the weight of the b is equal to 1 situations. So we are not defining here, it is only alpha and t. So b old plus alpha t is equal to b new, whereas here it is being represented in terms of a wi old plus alpha t into x of I. So that's how we have to take into consideration for wi, because this x of I is keep on changing. Here b is not the b which is suffix here is not changes. That's how we can consider as a 1. So here b new is equal to b old plus alpha into t. So this two thing is being derived till when y is not equal to t. The moment y is equal to t, then you will find that w new is equal to w old is going to generate. Then you no need to go further under this condition. So this is how the perceptance is going to work. Now normally in the university exam it is being asked about the perceptron and its mathematical derivations. So this is one of the important area for the discussions. For the easy way, you have to understand that there are three components here. One is sensory unit, another is which is input, association unit, which is the middle input point where this association unit will be collecting the inputs, and the response is an output. And the sensory unit is basically used for the used to collect the input x1, x2, x3, which is having a fixed weight 1, 0 or a -1, and binary activation functions is being used for in the sensory unit for processing the input weight input and through the corresponding weight w's, and the output signal is binary informations, and that binary information is being passed through the response with respect to the output activation functions 1, 0 and -1, and you are finding the y in, and thereby you are giving to the activation function to identify where it lies for the given input 1, 0 and a -1 point, and accordingly you will be having the learning build-up, and if that learning build-up is not equal to target, a weight is being adjusted based on the learning rate and the target. That's how this process continues. So this is what we see in the case of a perceptance condition. Now we see the perceptance learning algorithms. Now this is another very important area. The perceptance learning algorithm is suitable for a binary or a bipolar input. Now here what we do is then initialize the weight and the bias. Okay, we consider it as zeros. Now we are performing the stage 2 to 6 until we see that output y is equal to the target. Now step 2, perform 3 to 5. What is 3 to 5? 3 to 5 is this stage. In the step 3, first of all, we are taking an input layer applied to the activation function. X of I is equal to S of I. Now calculate the net input of so that we are calculating the y in. So y in is equal to bias plus summation of input and the weight. That is what we calculate. After summing, the next is nothing but the applying to the activation function to obtain the output. Now output is obtained based on the y in greater than theta, y in is less than theta, y in is less than theta, and y in between minus theta and theta. So that's how we can able to y in greater than theta, y in less than minus theta, and here minus theta less than y in less than theta. So under this range we are going to get this output y, and you have to remember this one. This y in is a positive values here. If you see now here, if the positive value is there, then it will be on this range. Now if the y in is having a stage with respect to the negative values, so it will be giving you these values. Now another important thing you have to note in this particular case of the activation function is that depending upon the conditions of the output y and the target, this process will continue. How this process will continue? Because the new weight is being formed. New weight is with respect to alpha and t. So once the new weight is formed and the new bias is formed, with respect to that new base and new bias, again what is going to happen, you are going to produce y in, and then again with respect to f of y, this particular factor is followed. This is how the learning pattern is being processed, and the model is being put for the training. And lastly, train the network until there is no change in the weight or stop. If the condition is not met, then it continue from the step 2. That is what 3 to 5 it is being stating. Now the training step 0 to 3, it is being stated exactly in this same form as the learning steps. So here also you are summing up, you are doing the activation function, verifying, and this particular process continue. Now if you see the flowchart with respect to the Perceptron case, now in the Perceptron flowchart, if you see, initially we initialize the weight and bias to 0. Then alpha, we are setting this value of alpha between 0 and 1, which is nothing but your learning rate, and we are taking a conditions in this one is the input synapse equate with respect to the target output. So we are taking the sensory unit. The sensory unit is same and the target unit. If the if we are taking sensory unit S is nothing but x of w. So x of w is equating with respect to the target. If it is the case for each particular case, so here what we are going for each particular case, we are going to check it. Now here we are for the first case, we are taking the input x of s1, and from here we are input x of I we are is equal to s of I. From here we are calculating y of I, that is we are taking all the x of I summing together to create a y of I, y of in, and from this y of in we are defining the y, which is the activation obtained after applying the activation functions. If it is a binary 0 and 1, if it is a bipolar binary 1 0 minus 1, and we are getting the y. So y is, you are get it from f of y in, and where f of y in case y in is obtained from x of I and w of I, that is s is nothing but x of w. So that is the situations. So here if you want to obtain this s is equal to target, we are following these conditions. If s is equal to target, if you are not needed, you can directly terminate. So for each s is equal s is with respect to the target, if this condition, if it is not equal to t, then what is going to happen? If y we are representing y in terms of representing in terms of representations suffix is equal to t. If this is not met, that is not equal to, then in that case a particular condition is indicating that this is not operations. So that means this is valid conditions. If y is equal to t means it is a terminating condition. Then in that case w nu is equal to w old. But if this is indicating the y is not equal to, that means y is not equal to target t, then in that case this weight has to readjust. So w nu is equal to w old plus alpha into t of x of I, and that's how b nu is equal to b old plus alpha of t. So this how we continue, and that indicates the new weight change, and then again it is going for it is verifying for the given s is equal to t. If it is needed, it follows, and once everything is completed, so this is satisfied, then it will be terminating, and it is going to stop. So that's how. So here you can see this one, initialize to 0, following the condition for each input to verify that it is producing an output, and that is related to the target t. And if that condition is not met, it is going for a weight adjustment, and this is a process. If it is met, then it is going to check whether the weight change is needed or not. If it is not needed, then it is going to terminate. So this is how the Perceptron flowchart is being functioning. So we have seen that in the case of a Perceptron network, the Perceptron neural network has given you the way for understanding in the case of how the weight is being adjusted for the given input, and thereby the error which is being generated, and that error is being used to adjust the weight. And by adjusting that weight, the two consideration is being taken. One is the learning rate alpha and another is the target. Based on the learning rate alpha and the target, the system we continue until it verify that target is equal to same as the the predicted output, and then the system terminate. So with this I come to the discussions conclude. We will stop here for the further discussion on the perceptrons, and in the next segment we will discuss on the perceptron with respect to the numerical problem. Thank you.